Thank you very much. Come inside, there's apparently plenty of room. Feel free to come closer as well, of course. So my name is Thomas, as was just said. I have the pleasure of being here in Kyiv for the first time. Really like it. My first time in Ukraine, actually. Let's get right to it here. Hang on one second. Oh, wait. Okay, I can fix this. So what we're going to talk about today is post-mortem debugging in Node.js. So before we get into what exactly post-mortem debugging is and why you should care about this, especially in Node.js, I thought I just wanted to introduce myself. My name is Thomas. I do a lot of open source stuff on GitHub. And I'm the principal software engineer at Elastic, where if you know Elastic, you probably know us from our products, not as much our company name, but we do stuff like Elasticsearch and Kibana and interesting things there. And I work with Node.js at Elastic. I'm also a Node.js core member, and I'm on Twitter. So actually, while they're playing music next door, I'm just going to tweet something because I prepared a tweet earlier with my slides. So there we go. Now I tweeted that. So if you look me up on Twitter, you can also get the slides. So if there's anything on the slides afterwards that you want to remember, I posted it on Twitter. So let's get going. Today we are going to talk about post-mortem debugging, as I said. So I'll just do a quick introduction to what post-mortem debugging is and why it's important. And a key part of post-mortem debugging is what's called core dumps, and I'm going to talk about what that is. Then I'm going to give an introduction to something called llnode, which is a tool that you use to analyze core dumps in Node. And then we're going to look a little bit about how we debug crashes and unresponsive processes and memory leaks. So that's the agenda. So at the Node.js Foundation, I'm a part of the Node.js Diagnostics working group. And this working group, the idea of this working group is to make Node.js better to diagnose, basically. That's what's right there in the name. So we make tools and APIs that you can use as a Node developer to figure out what's wrong or why your application is slow and stuff like that. And post-mortem debugging is one of the things we're working on. So what is post-mortem debugging? How many of you have heard about post-mortem debugging before? Not as many hands as I'd hoped, but that's good. That's why you're here, so that's perfect. So post-mortem debugging is almost like that. You remove bugs post-mortem. No, so if we ask Wikipedia what post-mortem debugging is, it says post-mortem debugging is debugging of the program after it has already crashed. And that is certainly true, but it's a little bit of a gray area because you can also, so a lot of the tools that we've developed to make it possible to do this can actually also be used to debug problems before your program crashes, in situations where other tools are not possible to use. So we'll also look at how you can use it not even only for crashes, but also for figuring out other things like memory leaks and stuff. So I mentioned tools. There's a lot of different tools out there. We're going to cover some of these today. LLDB and llnode specifically, but there's also an alternative called MDB and MDB v8. I guess you all try to use Chrome DevTools from time to time. There's also some nice features in there that we could take advantage of. So we'll get to some of these tools in this talk. So before we actually continue, I want to talk about core dumps. Core dumps are amazing. How many of you know what a core dump is? More hands, that's better. How many of you know why it's called core dumps? I'm happy because then I can tell you. So when I'm not doing programming, I really like figuring out why things are called what they're called, like the history of words and stuff. And core dumps is one of my favorite examples. So before we had solid-state memory in our computers, the way we stored things in memory in computers for a very long time, for a period of actually 20 years, was on these things. This is a magnetic core plane. So you're viewing it from above, but you could imagine in a big computer you would have many of them stacked on top of each other. And the reason why it's called a magnetic core plane is that if we zoom in, oh, by the way, this magnetic core plane contains 128 bits, not bytes, but bits. It's 32 times 32. And if we zoom in a little bit, we can see these small metal rings, the cores. That's why it's called a core plane. And it's ferrite cores, and they can store a magnetic charge, and you can actually measure the direction of the magnetic field, if it goes clockwise or anti-clockwise. And that's how bits were stored, and how you could then read out bits using sense wires. So if a programmer back in the days had a program that was not working like they expected, they had to look at how these bits were in memory to figure out the state of the program. So how do you do that? Well, you would basically read all the bits and dump them out onto a printer. So this is from an IBM 1401 system, and there is an IBM 1403 printer here. That's a big matrix printer. You would print out the entire content of memory, basically like a hex dump, and then you would sit and look at all the pages and figure out what the state of the program was. Luckily, we've come a long way since then. Today, we also have this data, but we store it in a file. Obviously, we don't print it out on disk, but we add some extra information. So we add information about what was the processor registers at the time of we took the core dump, for example, when the program crashed. We also have the program counter, so we know exactly how far where the program was. We store some system flags and a lot of other things. And today there's actually a few different core dump formats. The most common one is ELF, so that works on all modern Linuxes and BSD systems. But if you're using a Mac, you will probably be working with a core dump format called Mac-O, or Mac-O, I'm not entirely sure how to pronounce it. It's also the format you use for iOS devices, for example. So that's core dumps. So how do we get them? So on most Linux systems and Linux-like systems, like for example a Mac, there is this ulimit command. You can set it to tell the operating system that you want to capture core files. And the command, the argument you give it is the size of the core dump that you want to generate, the maximum allowed size, because of course these can take up a lot of disk space, and you don't just want to leave this on normally. So normally this is actually set to 0, but if you set this to unlimited, it will allow core dumps in the current terminal session. So if you quit the terminal session, it will go back to 0 again. And then if you are running Node, you have to tell Node when it crashes to actually generate one of these core dumps, or tell the operating system to do it. Because normally when Node crashes, it just exits with an exit code that's not 0. It actually doesn't send the correct signal to the kernel to let it know that you want to generate a core dump. So you use this flag, abort and uncaught exception. That means tell the operating system to send an abort signal. And that will then, if you had that other thing set, it will then generate a core dump, right? This is how you do it for crashes. But you can actually also use the gcore command on Linux and give it the process ID of the process that you want to generate a core dump of, and then you can actually do it on a running process. You don't have to wait until it crashes. And and that will then save a core file in your current working directory, and then you can take it off your production server and take it somewhere else and analyze it. If you're on a Mac, you can also use LLDB to do the same thing. This technically also works on Linux, but if you're on Linux, you probably want to use gcore because it creates a smaller core file. But it's basically the same thing. Generates a core dump if you run this command, and it saves it to this file that you specify here. Okay, easy. So now we can generate core files. So the next step is how are we going to actually analyze them? Because we don't want to just look at the hex dump, right? That's become a long way since then, luckily. So we use a debugger like the most popular one is called GDB. Unfortunately, we can't use that with Node. There's another one called LLDB. That's the one we most likely will use. There's also MDB that's been used in the past. But LLDB is like the new one we use for Node.js. And it runs on a lot of different operating systems. And by the way, for a while I was like, what is this database they're talking about? And I figured out, okay, it's debugger, not database. So that just shows you how smart I am. So how do you get LLDB? Well, if you have Xcode installed on your Mac, you already have it. It comes with Xcode. It will be installed in the background. If you don't want to install Xcode or you're not on a Mac, if you don't want to install Xcode or if you want to upgrade the version that you have, you can use Homebrew to install it instead. And there's a similar, you can use apt-get on Linux, etc. And then the next thing you need is llnode. llnode is a plugin for LLDB that allows LLDB to understand Node, because LLDB is a general-purpose debugger. It's used for debugging C code or compiles binaries, right? But it doesn't understand JavaScript. But luckily, it's extendable. So there's a plugin called llnode that we work on in the Diagnostics working group that gives it that capability. And normally, you would run LLDB like this. So you have a path to the program that generated the core file. That's actually important. So if you have a core dump, you need to actually also take the file that the program that crashed, for example. You need to take the binary of that off your production servers together with the core file, because when the binary was compiled, there is a lot of different debug statements that's actually compiled into the binary that LLDB uses to make sense of how the memory structure of the core file is. So you need both the binary and the core file. And the way you start it normally is LLDB, and then the path to the program, the path to the core file that works. And if we are using llnode, there's a little shortcut that you can use to load the plugin for you automatically. You just write llnode instead, and the rest of the command is the same. And it will just load this llnode plugin for you. So let's look at crashes. So normally when you have a crash, you get a stack trace. And hopefully that's enough to figure out what's wrong. You don't need a core file, a core dump. But in some cases, it might not be enough. Maybe your code is actually fine, but there was some state of the program was different than you expected. How you can't see the state of the program from just looking at a stack trace. Or maybe it's because this is JavaScript, everything is asynchronous. Maybe the stack trace just go back to like a process next tick, like it does here, and you're like, okay, you don't really know much. So that's where you want to be able to reproduce actually the whole system as it was running. So you need the source code, of course, to be able to reproduce, but you also need the state, as I said, and then you need the stack trace, the place where the program was at the time you took the core dump. So. Let's see. Yep. Okay. So I've loaded up a core dump that I called earlier because it takes a little while to generate the core dump and everything. So there's no reason to go through this now. And I started llnode with the node binary and the core dump, and I'm presented with a command line here called llnode. And so to get started, I can, for example, type help. And that shows me all, this is llnode. This is LLDB. So there's a lot of different commands you can give. We're not going to look at all these. But I can also type v8 help. And v8 is actually the plugin that we installed. So everything that's prefixed with v8, that will use that plugin. So you can see a type v8 help, and then there are some commands here. And for example, there is a command called bt for backtrace, so we can see the stack trace of when the crash happened. So if we just type bt is actually also like a normal command you can type in llDB. If you just type bt normal, we get like this stack trace here. And we can see there is some C++ code here and of the stack, so this is the top of the stack frame, but then there's a lot of blank stack frames. Can any of you guess what are the blank stack frames here? Why is there nothing? Why doesn't it say anything? Any ideas? No? So these are all the JavaScript code. llDB doesn't know JavaScript. So luckily, we can type v8 bt, and then look again. And then suddenly, we actually have the stack trace from our JavaScript. And not only do we have the stack trace, we can see here we have, so here we have the function onsave, what's called, and we can see a reference to a memory address, what this was set to, so we can actually inspect what this is inside the onsave function. We also can see that it was given 2 arguments. The first argument to the onsave function was null, and the second argument was an object. And oh, by the way, did you notice that this was frame number 6, right? So, okay, we can't do it clear. So we can say frame select 6, and now we selected frame number 6, and we actually see some assembler code that is kind of the code that's in frame number 6, but that doesn't look like JavaScript. So luckily we can say source. No, we have to say v8 source list. And then we actually get the source code of the onsave function, and we can see it takes 2 arguments, error and user. So we can actually see the JavaScript source code. Why can we see the JavaScript source code? Because in JavaScript, when Node runs JavaScript, the code is in memory. So the code is actually part of the core dump. The raw JavaScript code is in there inside the memory, right? So that's why we can actually see the code that was running at the time of the crash. But let's actually go back to the backtrace here, and then let's look at this argument here. Actually, before we do that, let's just look at the. Let's look at. I didn't show you. That's a mistake. I didn't show you the actual error. But the error was the stack trace that we originally got when the program crashed was cannot call first on undefined. So that was the error. And if we actually look at the code here, let's just go to demos. Actually, look at the code here. You can see it would error on this line 16. And you can say we're trying to access first on the name property on the user object, and that's where it failed. So if we go back to looking at the crash, and then look at this object here, the object is interesting because the object is the user argument that we are trying to work with. So that's where the data is located. And then we write v8 inspect, and then that memory address. We look at that memory address to see what's on the memory address. I don't know if you can see this. Let's do it like this. So you can see there is actually an object there, and it contains one property called name, something like that, N-M-A-E. So it's spelled wrong. The data was spelled wrong. And we can actually go further and look inside this object. V8 inspects this object, and then we can see that that object has 2 properties: first name and last name. So this is where the problem was. The data that was sent from the client had invalid JSON in it, or a JSON that was not as we expected it. So that's why the program crashed. We couldn't see that from just viewing the stack trace. We would have had to add a console log and do stuff like that to figure that out and redeploy. But here we can just figure it out immediately after the crash. Okay. So that hopefully shows how core dumps can be super useful for figuring out the state of the program when it crashes. Another thing that I just wanted to throw in here, even though it has nothing to do with core dumps, is I don't know if many of you, who, if you're Node developers, have ever tried to install this Node module called Node Report. I have some good news. You don't have to do that anymore. So Node Report is a program that is a module that you load inside your application, and then if your application crashes, it will print out a little summary of the state of the program. Not as much as you get on a core file, not the state of the program, so you can't see the data, but you can see a lot of useful information. So that's sometimes really nice to have in your system. But you don't have to do this anymore because as of Node.js 11.8, we actually rolled it into core. So now it's part of core. It's still experimental, but it's part of core. And you use it by using this command line argument, command line flag experimental report. It's just called report now. And you probably want to add a few other flags as well, because experimental report by itself doesn't really do much. So you want to add, for example, the uncaught exception that if the program crashes, it will write this report to disk. You can also add the onSignal. OnSignal means that you can send it a signal, it defaults to user 2. So you can send it a signal to generate a report. And on fatal error as well. So if Node crashes inside the Node C++ code, if it's not just like a JavaScript crash, if it's like a fatal error crash, buffer overflow, something like that, then you can also get the report. So just thought I would quickly show you what a report looks like. So, where did I put this? Oh, maybe I did put it inside crash. There we go, yeah. So it's just a JSON file, and it will be written to disk the moment your program crashes. And you can see you get some information about what triggered it, how the node was started, the process ID, the node version, the different subversions of node internals, the specific release, OS information, what OS you're running on. You get the stack trace, of course, but you also get the native stack trace. So you get a lot of information that you don't get normally when Node crashes. And this is, of course, a much more lightweight than a core dump is. But it doesn't contain all the information that a core dump does. But I still thought I wanted to mention it. So the next thing where core dumps is super useful is if you have a process that's just hanging. And you don't know why it's hanging. Suddenly, it just stops responding to requests or something like that. And the only thing you normally do is like, well, you terminate it and start it again and then hope it doesn't happen again. But that's not really the right solution. Well, you wanna figure out why actually that it's crashing, right? Or sorry, why it's just spinning, why it's not responding. So you want to ask yourself the question, what is it actually doing? And again, you can use a core dump to do that. So the way you would do that, so I have a, let's just try to go in. So I have a demo here, and So this is a very simple program. It's requiring a module called stringify, and then it's trying to make all the properties on the object into strings. So that's all it's doing. And if you try to run it, it just hangs. Nothing is happening. Apparently, we can't really see what's going on, but it just hangs. And so what we then do is we use our llDB command to attach to the process, and we generate a file called core. So now it's doing that, and now it's dumping all the memory to disk. And I'm gonna abort this because this takes forever. If I can. Of course I cannot. We'll let it run. That's fine. So while this is doing that, we will go to this other thing that I prepared in advance. So here I actually have that core file. And how do we know what a program is doing? Well, we look at the stack trace. We look at the program counter, right? We look at where it is right now. So we write v8 bt. Oops, scroll up a little bit. There, and we can see the stack frame number 1. It was actually running the stringify function. Obviously, in this case, it was a super simple program, so you could probably have figured out why it was looping without having to use a core dump, but this is just for the sake of the argument. So you can see this is the function that was executed when we took the core dump. So this is why it was something in there must be why it's spinning. So what we can do is we can go to, so as you can see, this is still like fantastic, right? So let's just exit this. Maybe we can't even do that. Anyways, we can luckily spin up a new. There we go. So if you look inside the stringify, that was the wrong one. Inside stringify here, we can see we have a while loop, and we're kind of iterating until the key is until there are no more keys. But obviously, when there's no more keys, we're going to have undefined instead of null. So that's why it just keeps running. So if we just change to this instead, it would work. So that's where our bug was, right? Alternatively, you of course could use CPU profiling. That's a very good alternative. CPU profiling, I'm not going to go into that here, but that's where you're asking the CPU like 99 times a second, what are you doing, what are you doing, what are you doing? And you basically get a stack trace for each time, and you could use the same thing. And there you would probably use something like flame graphs. If you look into flame graphs, that's an alternative way to get similar information. So just to recap, I have some slides here. We're not going to go over them now, but they're here. So if you're looking at the slides later, here's all the commands that we were running. So finally, memory leaks. Memory leaks is probably the hardest thing to debug in probably any type of application. And if you let them run long enough, you get an error like this in Node.js where it just runs out of memory. Well, it doesn't have to be a memory leak, but that's usually the issue, right? So what's a memory leak? So we have an object structure in Node.js. In JavaScript, there's also always like a root object, and all other objects are referred to from that object, either directly or indirectly. And then if one of the objects loses a connection to one of the other objects, that is now available for garbage collection. So that's actually not a memory leak. Because now the garbage collector can see, okay, nobody's referring to this, we can clean it up. The problem comes when we have, for example, an array, and we keep adding things to the array, but we forget to remove them again when we're done using the object inside the array. So just keep adding things here, and the object just grows and grows and grows. And this might be like normal operation, but in many cases it's probably not. I mean, of course, the problem here is you can see we don't know if this is you can't check if this is supposed to happen. So you as a developer have to step in and analyze and say, okay, we have this array and it contains 20,000 elements. It's only supposed to contain 10. That's probably where our memory leak is, right? So how we're going to use llnode to debug this? So you take a core dump, open it in llnode. You use a command called find.js objects. It will basically list all the objects and group them by type. So you have the instances, the total size of all the objects combined, and the name. And if you add -d to the end there, you'll also get a reference to like a memory address of an example of one of those objects. And if you scroll down to the bottom, we have all the ones that have a lot of instances at the bottom. And we, as a developer, we know our program, so we are looking at this called visit. There's 235,000 visit objects in memory right now. That's kind of strange, because we're not supposed to have that many. This is just supposed to keep a reference of the current active users on the website, and they're not supposed to be that many. So something is going on here. So we can say, okay, let's look at all the instances of visits. So we use find.js instances, and we see a lot of those. And we can take the memory address of one of them, like this one, for example. We can inspect it to see what it actually contains. We use the M property to get the map. The map is what's called a hidden class in JavaScript. So all objects have a hidden class behind it, so we can see the hidden class for this specific object. And we can see there's a visit ID, and there are some headers. And we can even look up the map and inspect that as well, and we can see what does this map look like. So we can get a lot of information about how Node stores the objects internally in memory. But what we really want to do is we want to use the find_refs command. Find_refs says, it looks at this visit object. We just took one of them. There's 250,000. We just took one of them. It's like, find all the objects that have a pointer to this visit object. So we use find_refs. And we see there's one. And it's an array, and that array contains a lot of objects. So that's probably where the memory leak is. Unfortunately, llnode can't right now tell you where this array is in your source code. Hopefully, that's something that can be added. But at least you now know as a developer where approximately to go and look. So how can this be improved? Because this is obviously, like last resort, this is pretty complicated to do. Well, if we could convert the core dump to a heap snapshot, then we could load it into Google DevTools, Chrome DevTools. That's not yet possible, but if any of you want to make a pull request to make that happen, that would be awesome. Alternatively, when we cannot do that, it would be nice if we could tell our application to trigger garbage collection and then make a heap snapshot right after the garbage collection have finished running and write it to disk. And we just landed something in core that makes this possible. And then if you have two heap snapshots, you take one heap snapshot and then wait an hour, take another heap snapshot. You can view the difference and see which objects grew in amount. Like suddenly we got 100,000 more visit objects. This is the first heap snapshot we take, then we wait 1 hour, then we take another heap snapshot, and then we basically look for the common ancestor of that diff. And the way you can do that is you can actually write this on Node 11, 13, and above. So you can listen for the user2 signal, for example. Could be any other signal. Then there is this new function called write heap snapshot that was added in Node 11. You require that from V8. And then if you started your app with expose GC to expose the garbage collector, you can actually trigger a garbage collection just before you write the heap snapshot. That's nice because then you don't get a lot of things that technically could have been ignored. Get a cleaner heap snapshot. And then you call write heap snapshot, which will return the name of a file that it wrote, so you can write it out to the console. And in the, there we go. Let's unskip this here. just gonna do live editing of my slides here, right? There we go. So the way that you then use these heap snapshots is to just take any tab in Chrome. It doesn't matter which tab it is. Just open a tab in Chrome with some other website on it. You go into the inspector, and you go into the memory tab in the inspector, and there's a load button where you can actually load a heap snapshot that you've taken. And because Node is using V8 inside, Google Chrome knows how to read heap snapshots from Node. So you load them up here on the side. So you load the 2 heap snapshots taken, for example, an hour apart or whatever, depends how fast your memory is growing. And then there's a little drop-down up in the left corner there where you can say, I want to do a comparison of 2 heap snapshots. So you select comparison mode. And then here, in that column that's called delta, you sort by that. So you have, in the very top, you have the type of object that has grown the most in memory. And then what you can then do is look in the bottom right corner of the screen here, and you can see, it's not very clear here. Let's see if can we zoom in here? Hang on 1 second. There we go. Almost got it. Can't see my cursor at the same time, so it's a little bit. There we go. So we selected an object here, and we can actually see where in our code that there is pointers to this object. So that basically gives us the same thing that we saw before with the core dump. So we find all the references to one of these objects that we selected. So this is a much easier to do than core dumps, but it requires that you have a heap snapshot. And you can't currently, there's no tools that I know of to convert a core dump to a heap snapshot. It's technically possible, you could do it, but somebody needs to write the code. So the same recap slide as before. We're not going to go too much into that. Instead, I want to talk about an exciting new thing that landed recently in llnode. And that is, previously, in this talk, until now, we've been using the CLI. We've been using llnode from the command line. But we landed a PR so that we could now also have an API, so you can use it from JavaScript. So you can load a core dump into JavaScript and actually get the objects back into JavaScript. And the way there we go. The way that works is that you require llnode. That is a module you install from npm install llnode. And then you call the from core dump, and you basically give it the same 2 arguments as you would normally give llnode on the command line. So it needs the path to the program that crashed and the path to the core file. And then you can get the process object. That's like the process object you're used to from Node. It's called process. And it will load that into memory, and now we will suddenly have a process object with a process ID that has the ID of the process that crashed. You also have access to a threads array, and this shows very well that actually Node is not single-threaded, as people sometimes say it is. There's actually threads behind the scenes in the event loop. And you can loop over these threads. And you can get the thread ID, and each thread, of course, has a state, like it was doing something at the time where you took the core dump. So you can loop over the stack trace for each of these threads and print them out. So you have access to the same data as that is inside the core file that you before used the command line to iterate over. Or you can, for example, get the heap, look at all the types in the heap, and print out all the instances of all the types in the heap. So you actually make some more clever tooling on top of this to make it easier to work with. And currently there is the API for this is located here on GitHub. There is a JS API markdown file in the root of the repository that you can look at to see the full API. This is still a work in progress, but I think this is going to be really exciting and allow people to write really awesome tools on top of llnode. So I just wanted to finish by talking a little bit about the Diagnostics Working Group. So the Diagnostics Working Group is a group of people under the Node Foundation, myself included, that work on tools like these, like work on llnode, work on other things in Node Core, as I said before. And all working groups in Node.js is just a repo on GitHub. So if you go into this URL here, github.com/nodejs/diagnostics, you'll be treated with the repo for the Diagnostics Working Group. But in here, we plan meetings. Every time we have a new meeting, we open an issue, and you can actually join the meeting. There's a URL for Hangouts, and you can we stream the meetings live on YouTube as well if you just want to follow along. And you can see the different things we are working on. And speaking of working on, we work on tracing, profiling, heap and memory analysis, step debugging, and, of course, post-mortem debugging. And just some examples of some things we recently landed in Node Core. There was the diagnostics report that you just saw. There is the get heap snapshot and write heap snapshot commands that we also just saw. And then there's another one I haven't covered here, but I thought I wanted to mention it, which is super, super cool. Monitor event loop delay. So if you're putting too much work on the event loop, because the JavaScript is still running in one of the many threads, it can only do one JavaScript operation at a time. If suddenly one of these functions takes too long to run, takes 100 milliseconds to read some JSON, you're blocking all the other things. So monitor event loop delay will allow you to get notified when this happens, when suddenly your event loop becomes slower than it's supposed to. And so what we're currently working on, there is a ton of stuff here. Some of them are names you probably already know, like async hooks, but it's still not done yet, so we're still working on that. We're working on some really cool thing about time travel debugging. Continuation local storage. Have you ever used the CLS module on NPM? Yeah? I can tell you we are working on getting that into core now. So there is no more you have to hunt for the right fork of CLS to figure out one that works with your version of Node. We're working on putting that into Node Core. So a lot of other really cool things. These are just kind of like the highlights. And here's a free idea. Like if you want to contribute, this is probably one of the harder ideas, so I don't blame you if you don't know how to do it, because I don't know how to do it. But if you could figure out a way to extract a heap snapshot from a core dump so we can get it into Chrome DevTools, that would be super, super awesome. And with that, I want to say spasibo, sorry. Any questions? Yeah.
Thank you for the great report. It was really interesting, at least for me, super interesting. I'll try everything by my own after the conference. About the problem of getting a heap snapshot. I understand if we're talking specifically in the case of failing process, not in the case of memory links, why can't we just monkey punch the array constructor and take the memory heap at the moment of the error creation?
What constructor, sorry?
Error constructor.
Ah, yes. Well, you could do that. That would be a lot of disk space, because all the memory is being written to a file every time, and you are making a lot of errors all the time that you not necessarily want to. They are not like errors that are crashing the program. They're just errors that you're passing around your program that are okay. Like you can recover for them easily. There's no problem. So there'll probably be a lot of disk space to spend on that. But anybody could technically just monkey patch it, and you would have that. So you could make a Node module that did it, but I don't think it's something that would make sense necessarily to have as a default thing in Node. Maybe I'm wrong, but that's my idea.
No, of course not the default value thing in Node. I mean, but like solving the problem, specifically when I'm, for example, searching for a bug and my program is crashing, I can have this at the crash moment.
Yeah, so there actually the heap snapshot isn't that useful. The heap snapshot is mostly useful for debugging memory leaks because the heap snapshot only have it doesn't have the entire state of the program. Like it doesn't have the stack where the program was at the time of the crash. It only has the data in memory. So for that, you need something like the core dump to get the actual state of the stack and the arguments that was called that you called with the function with and stuff like that.
Okay, thank you.
Hi. First of all, thanks. It was awesome. I have two questions. What is stupid one and the normal one? The stupid one, what that code does where you import VA and global.gc? Does you trigger garbage collector to clear the memory?
Yeah. So normally the V8 garbage collector will just run periodically in the background when it thinks it needs to clear up the memory. And actually, it's lazy, so it will only do it when it's about to run out of memory. But if I understand correctly, at least, I'm actually a little bit unsure about this, but I think it's important to run it before you take the heap snapshot to be able to not get a lot of noise from the objects that could have been cleaned up. But actually, it's a good question. I might be wrong on that one, that actually the heap snapshot doesn't contain the objects that are not referenced, if that makes sense. So maybe you don't have to do that. I have to look that up, actually.
Okay, and the normal question, you mentioned about threads, and it's awesome. The question, does it related with worker threads? New feature, experimental one, relatively new feature, but still not released, still not in stable status.
That's a very good question. So yeah, as you said, we just released in experimental still worker threads that allows you to take some work and put onto threads in JavaScript, which wasn't possible before. So those will show up there as well, actually. And actually, currently, this is the only way to properly debug those worker threads, because all the existing debug tools out there doesn't actually know how to handle threads yet, because it's so new. But because this is so low level, it's fine. It can perfectly understand worker threads as well, because they're just a thread like any other thread.
Okay, how it differs from that 4 threads, which is default one from libuv thread pool, that sets, how it differs? The new ones, custom ones, and that standard ones.
Yeah, so the standard ones, so the way Node works with async code is that it has the event loop. So every time you do an I/O operation, for example, fetching a file from the disk, it actually, in the background, puts that on a different thread that fetches the data. And then when the data is fetched, it will call your callback on your main thread, so to speak, like your JavaScript thread. So only one of the threads normally is running your JavaScript code. The other threads are reserved for doing mostly I/O-based stuff, also a little bit of crypto and stuff like that. But you're not allowed to schedule work on that. Well, you do it indirectly by saying, I want to encrypt this, or I want to read this file asynchronously. So indirectly, you're of course scheduling work on the threads, but you can't take a piece of JavaScript and say, hey, run this JavaScript on this thread. You cannot do that. And this is where worker threads come in. With worker threads, you can actually say, I have a piece of JavaScript that's super CPU heavy. I don't want to block my main thread while I'm running this JavaScript. Put it on this other thread, and then report back when you're done. That's what the worker threads are for.
Thank you.
Any more questions? I think there was maybe a hand there, no? Okay.
So it's the end.
Yep. Thank you very much.
Thanks one more time, our speaker.